Okay, so this week we are looking at 11.6, absolute convergence and the ratio and root tests. The section is quite a bit shorter than the other ones that we spent two lectures on. So I'll still do it in two lectures. So this recording will cover the first half, and the next recording, which I'll load a little later this week, will cover the second half. And then I still owe you a recording for example 14 in section 11.1, which I might do this week as well, since we've got a bit of extra time. Okay, so if you look back at what we've done over the last few sections now, we firstly defined what we meant by sequence, and then we defined what we meant by series, and for both of those concepts we defined what we meant by convergence. Then in the sections after 11.1 we basically look at various tests that can determine whether helps us to determine whether a series is convergent or divergent. And so we continue with this trend. In this section we look at two additional tests called the ratio and the root test for determining convergence of a series, and in order for us to understand how these work, I need to introduce two new convergence concepts, and these are the ideas of absolute convergence and conditional convergence. So, suppose we've got a series AN. Now, we can consider another series which is related to the series, in which instead of looking at AN, each of the component terms of the series, we look at the absolute value of that AN. So the original series is the sum from 1 to infinity of AN, and this new series, this series that we're going to look at in this section, is the sum from 1 to infinity of the absolute value of each AN. Right? And these are the absolute values of the terms of the original series. And we'll see that by looking at this particular series, we can get an additional test for convergence of a series. Okay, so a series, our first definition for the section is, a series is called absolutely convergent if the series of absolute values is convergent. So, simple, straightforward definition. Notice that if we start off with a series in which all the terms are positive anyway, then obviously the absolute value of a positive number is the same number. Then in fact we get the same series that we started with. Right? And so absolute convergence in that case is the same as convergence. Is the same as convergence. Excuse me. Let's look at an example. Look at this series. It's minus 1 to the n minus 1 divided by n squared. The nth term. So an here is minus 1 to the n minus 1. And you can see, because of the minus 1, we're going to have signs that alternate again. But this series is absolutely convergent, because if I take the absolute value of each term, then I get the sum from 1 to infinity of 1 divided by n squared, which is 1 plus 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. And we know that that is a convergent series because it's the P series with P equal to 2, right? And so this is an example of an absolutely convergent series. Let's look at another one. Let's remove the square in the denominator. And now we've got what we call the alternating harmonic series. So it's negative 1 to the n minus 1, in this case now divided by n, not divided by n squared. Now, how is this going to differ from the previous one? Well, let's look again at the series made of the absolute values of this series. Well, the series itself, as you can see, will have alternating signs. So it's 1 minus a half plus a third minus a quarter and so on. And we know from the previous section that this is in fact a convergent series. However, it's not absolutely convergent, because if I look at the corresponding series of absolute values, then I get the sum from 1 to infinity of 1 divided by n, which is in fact our old friend the harmonic series, and we know that the harmonic series does not converge. So, what have we got now? From this example we can see that it's possible for a series to be convergent but not absolutely convergent. We will call such a series conditionally convergent. If a series is convergent but not absolutely convergent, then such a series is called conditionally convergent. Now, in the last example, we had an example of such a conditionally convergent sequence. So in other words, I'll reiterate it, it's possible for a sequence to be convergent but not absolutely convergent. However, it's not possible for the converse to hold. In other words, if a series is absolutely convergent, then it must be convergent. And we're going to look at the proof in a minute or so. Before we do, let's have a look again at what this implies. If you think about it, this means we now have an additional way of proving that a series is convergent. Because if I can prove that a series is conditionally convergent, then it must be convergent as well. So, a series can be convergent but not conditionally convergent. But if a series is a series can be convergent but not absolutely convergent. If a series is absolutely convergent, then it must be convergent. So let's prove that fact. So we'll start off with this inequality. Let's see why this is the case. Well, an is either positive or negative or 0. If an is 0, then the absolute value of an is 0. Then that inequality is essentially saying 0 equals 0 equals 0. If an is not 0, then it's either positive or negative. If an is positive, then an is equal to the absolute value of an, in which case an plus its absolute value less than or equal to 2an is obvious, it's equal to it, and it's greater than 0 because we assume that an is greater than 0. Alternatively, if an is negative, then an plus its absolute value will give us 0, in which case the inequality on the right hand side also holds. So we can see now that for any term in any sequence, it is the case, in any series, it is the case that 0 is less than or equal to an plus the absolute value of an, less than or equal to 2 times the absolute value of an. Right, now we can continue. Now, remember, we want to prove that if a series is absolutely convergent, then it's convergent. So let's assume that the series AN is absolutely convergent. So if the series AN is absolutely convergent, what that means is that the sum of the absolute value of AN is convergent. And now I can simply multiply by 2, take the 2 inside the sum symbol and get the sum of 2, absolute value AN, is also convergent. But now I can introduce sums now. So if the sum of 2 absolute value AN is convergent, then the sum of AN plus absolute value AN is less than or equal to the sum of 2 absolute value AN, which means the smaller one must also be convergent by the comparison test. And now we simply write the sum of AN as the sum of AN plus the absolute value of AN minus the sum of the absolute value of AN. Notice we can do this only because we know the 2 expressions on the right of the equality sign there actually refer to convergent series. If we didn't know that they were referring to convergent series, then we wouldn't be able to use those theorems, right? The theorems for convergent series. And now the sum of AN is the difference of 2 convergent series, hence it must be a convergent series itself. Also coming from the theorem on the theorem on convergent series. Example 3. Let's look at this one. Determine whether this series is convergent or divergent. Now, here we are taking cosine of n as n increases. Now remember, we are assuming, as we did in the 1a and 1b course, that the input to these trigonometric functions are radians. So when n equals 1, we're calculating cosine of 1 radian. When it's 2, it's cosine of 2 radians, and so on. We want to know whether this is a convergent or divergent series. When you do the calculation, you will find that the series has both negative and positive terms, but it's not an alternating series. For it to be alternating, the terms must be alternately negative and positive. In other words, one positive term, then a negative term, then a positive term, then a negative. If you go and calculate this, you will find that the first term is positive, then you've got 3 negatives, then 3 positives. And so the signs do not change in the way that an alternate sequence, an alternate series changes. We can apply the comparison test to the series of absolute values. We can say, well, the sum from 1 to infinity of the absolute value of cosine n divided by n squared is the sum from 1 to infinity of the absolute value of cosine n divided by n squared. And we know that the absolute value of cosine n is less than or equal to 1 for all n. And so we have the absolute value of cosine n divided by n squared must be less than or equal to 1 divided by n squared. Notice that the n squared is positive, and because of that, we don't change the direction of the inequality. At this point, we spot that on the right-hand side, if we take the sum, we've got a convergent P series. And so the sum of the absolute value of cosine n divided by n squared is convergent by the comparison test. Hence, the series, the sum of cosine n divided by n squared is absolutely convergent and therefore convergent by theorem 3. Okay, so now we will encounter our first test. It's called the ratio test, and it helps us to determine whether a series is absolutely convergent. If you have a series, the sum of an, if it turns out that the limit as n goes to infinity of the absolute value of an plus 1 divided by n is equal to a number L, which is strictly less than 1, then the series, the sum from 1 to infinity of an, is absolutely convergent and therefore convergent. If the limit as n goes to infinity of the absolute value of an plus 1 divided by an is equal to L, which is strictly greater than 1, or the limit as n goes to infinity of the absolute value of an plus 1 divided by an is infinity. In other words, that expression grows larger and larger as n grows larger and larger, then the series, the sum from 1 to infinity of an, is divergent. Finally, the third part of the test. If the limit as n goes to infinity of the absolute value of an plus 1 divided by an is 1, then the ratio test is inconclusive. And that means it could go either way. The test doesn't give us any information about the convergence or divergence of an. The proof is also quite straightforward, and we'll do it quickly. We'll use the comparison test again to show that the given series converges. Remember, in condition 1, for the first part of the test, we are assuming that the limit as n goes to infinity of the absolute value of an plus 1 divided by an is equal to a number L, which is strictly less than 1. Now, since L is a number less than 1, we can pick a number R, which is in between L and 1. If you think about it, that's always possible for real numbers. So you could in fact take 1 minus L divided by 2 and add it to L. You will then get a number which is exactly halfway between L and 1. So the point is, it's possible to pick such a number R. Now, for this number, we have that the limit as n goes to infinity of the absolute value of an plus 1 divided by an is L, and that L is less than R. That definition of the limit means that this expression an plus 1 divided by an, the absolute value of it, gets closer and closer to L as R grows larger. Which means, since R is strictly greater than L, at some point that expression, absolute value an plus 1 divided by an, must be less than R. We must hit such a point. And so we will be able to find a natural number n with a property that the absolute value of an plus 1 divided by an is less than R whenever n is greater than or equal to capital N. Now, the absolute value of an plus 1 divided by an is the absolute value of an plus 1 divided by the absolute value of an. And so we get the absolute value of an plus 1 is less than the absolute value of an times r for all n larger than capital N. And now we can do this for all larger n. So we start at capital N, we go to n plus 1, n plus 2, and so on. We plug it into the equation that we have, and we can see that an plus 2 must be less than an plus 1 absolute value times r, which is less than an absolute value of an times r squared. And the same thing for r cubed. And in general, we've got that n plus k less than absolute value of an times r to the k for all k greater than or equal to 1. Now this should begin to remind you of a geometric series. Alright? So n from 1 to infinity of a capital N absolute value r to the k looks like that. And that's a geometric series where the first term is an times r, and the common ratio is r. And so because r is less than 1 and greater than 0, we know that that series must converge. But the series from 1 to infinity of the absolute value of an must also converge. Why? Because the series we started with, the one that goes from capital N plus 1 to infinity, is the same series as the one we're looking at now, the one that starts from 1, except for a finite number of terms. N terms, in fact, capital N terms. And we know that a finite number of terms cannot affect the convergence or divergence of a series. And so therefore the sum of an is absolutely convergent. What about the second case? Well, here the absolute value of an plus 1 divided by an converges to a number L which is greater than 1, or it just grows larger and larger as n grows larger and larger. So then the ratio will eventually be greater than 1. It must be greater than 1, right? Eventually. And so we can find an integer n with a property that the absolute value of an plus 1 divided by an must be greater than 1 whenever n is greater than or equal to capital N. But that means the absolute value of an plus 1 is greater than the absolute value of an whenever n is larger than or equal to capital N. So if you think about this, under these conditions, if the absolute value of the next term in the series is growing larger, it's larger than the absolute value of the previous term, then that series, the sequence, cannot converge to 0. The limit as n goes to infinity of an cannot be equal to 0. And by the test for divergence, it means the series, the sum of an, diverges. We haven't looked at the third case because the third case we will discuss now as a note. Part 3 of the ratio test says if that limit turns out to be exactly 1, then the test gives us no information. So what we'll do is we'll look at two cases. We'll look at a case where the limit is 1 and the series is convergent, and the limit is 1 and the series is divergent. For example, look at the convergent series, the sum of 1 over n squared. Then the absolute value of an plus 1 divided by an plug it in. It's 1 over n plus 1 all squared divided by 1 over n squared. Simplify it to get n squared over n plus 1 squared. Now, what we are interested in is the limit of that expression as n goes to infinity. So we will divide again numerator and denominator by the highest power of n in the numerator. And when we do that, we get that the limit is 1. So that expression goes to 1 as n goes to infinity. And now we know that that is a convergent series. So here we've got an example of a convergent series where the limit, the testing expression, the limit of that test expression goes to 1, is 1. On the other hand, look at the divergent series, the harmonic series. For that one we have the absolute value of an plus 1 divided by an is 1 divided by n plus 1 divided by 1 divided by n, which is n divided by n plus 1. It also goes to 1. And so here we've got one example of a series that converges and that testing limit is 1, and one example of a series that diverges and that testing limit is also 1, which means these examples now show you that in the ratio test, if it turns out that the limit as n goes to infinity of the absolute value of an plus 1 divided by an is 1, then the test gives us no information. The series could be convergent or divergent. In this case, we've got a different test. Okay? Test the series, the sum from 1 to infinity of minus 1 to the n times n cubed divided by 3 to the n for absolute convergence. Another example. We'll use the ratio test, and our an in this case is minus 1 to the n cubed divided by 3 to the n. So the absolute value of an plus 1 divided by an looks like this. An plus 1 in the numerator, right? An in the denominator. And I can simplify this expression. I get n plus 1 cubed divided by 3 to the n plus 1 times 3 to the n. I can simplify the part with the 3's and just get 1 3 in the denominator remaining. I get 1 divided by 3 times n plus 1 divided by n, all cubed. And again, I can divide, when calculating the limit, I can divide by the highest power of n in the denominator and see that this limit goes to a third, which is less than 1. Because it's less than 1, the given series is absolutely convergent. Because it's absolutely convergent, it must be convergent. Example 5. Test the convergence of the series, the sum from 1 to infinity, of n to the n divided by n factorial. Since the terms an equals n to the n divided by n factorial are positive, we do not need the absolute value signs. So in this case, the term, the absolute value version of the sequence of the series is the same as the series itself. And so n plus 1 divided by an is n plus 1 to the n plus 1 divided by n plus 1 factorial times n factorial. How can we simplify this? Well, I can see the n plus 1 factorial in the denominator. It's going to be n plus 1 factorial, or it's n plus 1 times n factorial, we can cancel the n factorial and the n plus 1, and we get n plus 1 divided by n raised to the power n. And that's one of those expressions for the limit of that as n goes to infinity. Remember, that was one of the expressions that generated the number e in the Maths 1a module. And so e is bigger than 1, and so the series is divergent by the ratio test. Although the ratio test works in example 5, an easier way to see that the series is divergent would be to use the test for divergence, since an is equal to n to the n divided by n factorial. N to the n is n factors of n, right, in the numerator, and 1 times 2 times 3 up to n. Now that's obviously greater than or equal to n, right? Yes. And it follows that an does not approach 0 as n goes to infinity. Therefore, the test for divergence says that the given series is divergent. Now we've got another test which is convenient whenever we have a situation where we've got nth powers coming up in the expression for an. And this is called the root test, the nth root test, or the root test. And it goes like this. If the limit as n goes to infinity of the nth root of the absolute value of an is L less than 1, then the series, the sum from 1 to infinity of an, is absolutely convergent and therefore convergent. If that limit is L a number greater than 1, or if that expression, the nth root of the absolute value of an, grows larger and larger so that it goes to infinity as n goes to infinity, then again the series diverges. And finally, again, if the limit as n goes to infinity of that expression is 1, then the root test is inconclusive. As in the previous case, it means it doesn't tell us anything about the convergence of the series. Notice that if the limit as n goes to infinity of the nth root of the absolute value of an is 1, part 3 of the root test says that the test gives no information on the convergence or divergence of the series, the sum an. In other words, the series may converge or diverge. It turns out that if L is 1 in the ratio test, you might as well not use the root test either, because it will give you 1 again. Similarly, if L is 1 in the root test, the ratio test will also be inconclusive. Example 6. Test the convergence of the series, the sum from 1 to infinity, of 2n plus 3 divided by 3n plus 2, all raised to the power n. Solution. Here, the nth term, an, is 2 to the n plus 3 divided by 2n plus 3 divided by 3n plus 2. We think of an as being that term. Then the series is, then we can introduce now the expression that we want. So the square root of the absolute value of an will be 2n plus 3 divided by 3n plus 2. And now we need to take the limit as n goes to infinity of that expression, which turns out to be 2 over 3, which is less than 1, and hence it converges by the root test. Rearrangements. So quite an interesting thing that happens is something very counterintuitive when you rearrange the terms of a series. Now, if you think about it, remember I said to you in the second lecture, the lecture on series, that as soon as we start talking about an infinite number of terms that are added to give a sum, that we are talking about something that's quite different from what we had before when we add a finite number of terms. And so it turns out that something quite counterintuitive happens. If you take a finite sum and you rearrange the terms, doesn't matter how many terms there are, as long as it's a finite number of terms, rearranging the order in which you add or subtract them doesn't make a difference to the final answer. Well, it turns out that it does actually make a difference for an infinite series. By a rearrangement of an infinite series, the sum of an, we really mean a series obtained by changing the order of the terms in the series. So suppose we had a series, the sum an. We can now rearrange the terms. We can say, I'm making a new series now, and I want A1 still to be first and A2 second, but the next one I want to add is A5, and then A3, and then A4, and A15, and A700, or A6, right? And this is what we mean by rearrangement. Instead of taking the series terms in the way that they are, we rearrange them, right? So if it is the case that the original series is absolutely convergent, then any rearrangement will have the same sum. So if the sum of an absolutely convergent series is S, then the sum of any rearrangement of the series an will also be S. But if a series is conditionally convergent, then it's possible to rearrange the terms of that series to give a different sum. Let's look at an example. If you look at the alternating harmonic series, 1 minus a half plus a third minus a quarter and so on, when you take that sum, it turns out that it's equal to ln of 2. Now what we're going to do is, let's multiply. Now remember, because the expression on the left hand side has a finite answer, is a finite number, we can multiply both sides of these expressions by a number, by any number. That's what those theorems on sums, on series, tell us. As long as we know that a series converges, we can do addition and multiplication by real numbers, addition of two series, and so on. Right? And so now we're going to multiply equation 1 by a half. Now we get a half minus a quarter plus 1 over 6 minus an eighth and so on must be equal to 1/2 of ln 2. And now let us insert zeros between the terms of the series. And we obtain this expression. We're adding zeros, so we're not changing the left hand side, and so we leave the right hand side the same as well. So the one with the zeros is the same as the one labeled 2. And so now we can add the series in equation equations 1 and 2, and we get the following. We get 1 plus a third. Now notice the negative a quarter from equation 1 and the negative a quarter from equation 2 gives me negative a half. Right? Then the 1 over 5 plus 0 gives me a fifth. And the negative 1/6 plus 1/6 gives me 0. The negative, the 1 over 7 stays there. The negative 1 over 8 and from equation 1 and the negative 1 over 8 from equation 2 gives me negative 1 over 4, and so on. And so I'm using all the terms on the left on for both equations. And now I can add, on the right hand side I get ln 2 times 2 over 3, because it's 1.5 of ln 2 times ln 2. And so now I get 1 plus a third minus a half plus a fifth plus minus is equal to 3 over 2 times ln 2. But notice that the series in 3 contains the same terms as in 1, but it's simply rearranged so that we've got one negative term occurring after each pair of positive terms, but the sums of these series are different. Very interesting. And so it turns out that this can always be done. Bernard Riemann, also a famous mathematician who lived in the 1800s, proved that if the series AN is conditionally convergent and R is any real number, then you can find a rearrangement of the sum of AN that has the sum equal to R. And that ends the section. For Thursday's lecture I might do example 4 from 11.1. But this is everything that you need for 11.6.